Hello, I'm George Simantiris, PhD student at the Management Science and Technology Department of the Hellenic Mediterranean University. I will present to you our joint work with Professor Kostas Panagiotakis titled Unsupervised Deep Learning for Flat Segmentation in UAV Imagery. After a short introduction and a quick overview over the literature and the problem formulation, we will have a closer look at the methodology and the experimental setup before presenting results. We will finish with conclusions and future work. So, we all know that natural disasters are events that cause great damage or loss of life. In recent years, climate change and escalating weather phenomena facilitate natural disasters. Response and aid strategies play a vital role in minimizing the impact of disasters on both human population and environment. We have chosen to focus on flood because, as you can notice from the green bars in the first diagram, it is the most reported natural disaster in the recent decades and, according to the second chart, floods together with hurricanes inflict the most damage. Over the years, there have been different approaches presented to tackle the problem of flood detection and segmentation. We can essentially divide these approaches into unsupervised methodologies, which mostly utilize traditional computer vision and pattern recognition techniques such as probabilistic methods, k-means clustering, and region growing, and supervised methodologies, which are mainly based on deep learning and represent the current state of the art in performance. Both leverage diverse modalities like satellite images from the Sentinel and World View satellites, synthetic aperture radar, and UAV images. As we have seen, floods inflict significant damage on human lives and infrastructure. Effective flood detection and segmentation play a critical role in mitigating these impacts, and state-of-the-art flood segmentation techniques predominantly leverage deep learning approaches which require substantial amounts of labeled data for effective training. However, ground truth annotation is a labor-intensive process that typically involves 2 or 3 human experts and is prone to errors. This highlights the need for efficient and accurate methods for flood segmentation that reduce dependence on manual labeling. Tackling this problem, we present a novel unsupervised deep learning method for flood segmentation in UAV imagery where there is no need for ground truth. A schematic overview of the proposed methodology is shown in the figure. From the training images, a completely unsupervised algorithm automatically generates labels, named pseudo-labels, as masks for the training and validation sets. These pairs are then utilized to effectively train a deep learning architecture. The trained weights are used to predict the flood segmentation for images never before seen by the network. The inference is generated in less than 1 millisecond, and thus it can be applied also in real time. To generate the pseudo-labels, we have used an adjusted, unsupervised color-based flood segmentation method named UFS-HDREM, previously published by us. This method uses the RGB vegetation index, edge and color information from the LAB color space to construct binary masks with areas classified definitely as non-flood, leaving a remaining area which could be flooded or not, called potential flood area or PFA. The RGB vegetation index identifies visible vegetation using a green reflectance, which therefore cannot be flooded. And in the LAB color components, the flood has significantly higher pixel values than the background, which is determined by an automatically computed threshold for each image. In the PFA, a flat dominant color is estimated using a weighted probability map approach and an adapted hysteresis threshold with 2 tunable parameters T-low and T-high through probabilistic region growing yields the final flat segmentation, which will serve as pseudo-label. By adjusting only T-low, we obtain different values in recall and precision, and therefore a plethora of pseudo-labels from the same area. For the deep learning architecture, we have opted to employ two deep convolutional neural networks widely used for semantic segmentation for comparative reasons. The UNet and the fully convolutional network with a ResNet-50 backbone as published by Ronneberger and Long et al. Respectively. The first, with feature map concatenations from the respective levels of the decoder and encoder, features approximately 31 million trainable parameters, and the latter, with skip connections and residual blocks, comprises approximately 33 million trainable parameters. Our experimental frameworks consists of two datasets. The first, flat area dataset from which the pseudo-labels are produced, is used for training and comprises 290 color images, while the second, flat semantic segmentation dataset, is used for evaluation purposes only and consists of 663 color images. We haven't changed anything in the network's architectures and trained for 50 epochs with RMS propagation and cross-entropy loss using simple augmentation techniques such as vertical flipping, rotation, and uniform random noise. For validation accuracy, we opted for the dice score. Our goal was to observe if the networks could be trained with the pseudo-labels. The results were more than satisfactory. As we can observe in the tables with the metrics, for each set of different pseudo-labels we have used in the training process, original UFS HDRM method as well as variants A to E by adjusting the T-low as shown in rows 1 to 6 of the tables, accuracy and F1 score came close or even surpassed, in the case of the UNet, the corresponding metrics for the training with the actual ground truth. Thus, the ResNet-50 achieved a better accuracy when trained with the pseudo-labels and an F1 score which is 0.1% short as in the training with the actual ground truth. The UNet, though, performed 1 and 0.9% better in both metrics when trained with the pseudo-labels. The F1 score was calculated using the formula with precision and recall, while the overlined F1 score is the average of the F1 scores of all images. Our proposed method proved to be robust, coming close or even surpassing the training with the actual ground truth, the first two bars in the chart, when trained with different sets of pseudo-labels, and was consistently over the F1 score that the unsupervised label generator algorithm UFS-HD-RAM achieved. The orange bars in the chart denote the UNet, the yellow bars the FCN ResNet-50, and the blue bars the UFS HDRM algorithm. Therefore, we can conclude that the networks are capable to cope and correct false pseudo-labels. Furthermore, we present original images in the top row and the respective top segmentation from the 20th, 40th, 60th, and 80th percentile of the descending sorted F1 scores of the UNet predictions in the bottom row. Flat segmentation is overlaid in blue color, and each image's F1 score is also stated. The results, as you can observe, are very qualitative. Here we showcase more segmentation results with original images, top row of the left image cluster, and the actual ground truth, bottom row of the left image cluster, in comparison with the UFS HDRM method, the UNet, and the FCN ResNet-50 inferences. We used the descending sorted differences between the best performing UNet and the UFS HDRM method segmentations and selected the top 0th, 25th, 50th, and 75th percentile image. Again, flat segmentation is overlaid in blue color, and each image's F1 score is also stated. As we can notice, there are examples where the networks cope for false pseudo-labels, where UFS HDRM has failed, but the networks correctly predict the flat as shown in the first column of the right image cluster. There are a few cases where the networks fail, as shown in the last column of the right image cluster, where falsely areas of the sky are segmented as flat, which are currently under investigation so that we can understand why and thus correct them. To conclude the presentation, we have presented to our knowledge the first fully unsupervised deep learning approach designed for flat segmentation in color images captured by UAVs. We have utilized a pattern recognition method which automatically generates flat labels and trained two deep convolutional neural networks with these pseudo-labels instead of actual ground truth. We have obtained high-performance results surpassing the automatic pseudo-label generator algorithm and achieved metrics close to or even better as when training with the actual ground truth. There is a lot of potential for future work. We are currently working towards developing a process to further discard unreliable pseudo-labels. Also, we seek to create a specialized deep learning architecture and a customized loss function directing the network's attention exclusively towards the plot. Thank you very much.